So this is the plan for the 4 lectures. We'll see exactly how it goes. But today I'm going to review the description of the SYK model, and in particular its description by a set of collective fields and how it can be analyzed that way at large N. In the next lecture tomorrow, I'll talk a little bit about a 2-dimensional theory of gravity called Jaquev-Teitelborn gravity, or JT gravity. And this theory is related to a limit of the SYK model, as we'll see. And I'll discuss some applications in JT gravity, both thinking about it as a gravity theory and its relation to SYK. Then in the third lecture, the day after tomorrow, I'm going to review some aspects of random matrix theory and how some of these things are related to the SYK model, how they can be seen in the SYK model. And the next day, we'll discuss some of those issues from the perspective of JT gravity. This part is actually based on work in progress with Phil Sod and Steve Schenker. Okay, so let me start by defining the SYK model. So this is a quantum mechanical theory of n Majorana fermions. So 0 plus 1 dimensions, theory of n Majorana fermions. So Majorana fermions in quantum mechanics are very simple. They're just a set of matrices. So Majorana fermions we'll label psi I, where I goes from 1 up to n. And they're just a set of matrices that satisfy the anti-commutation relation psi I with psi j is equal to delta ij. In other words, they satisfy the anti-commutation relation of Dirac gamma matrices in n dimensions. But that interpretation isn't essential. They're just a set of matrices that satisfy this property. And there are various related ways of constructing them. So we can build them out of tensor products of Pauli matrices. So for example, we can do the following. I'm going to use this notation for Pauli matrices, where the matrices that are normally called sigma x, sigma y, and sigma z, I'll just call x, y, and z. And the subscript will denote which of a certain collection of spin operators they're acting on. So we'll have some collection of spins. There will be Pauli matrices for each spin. So this is the Pauli X matrix acting on the first spin. So these are the first two. Then we can define more. To define psi 5 and psi 6, you would put z1, z2 times x3, z1, z2 times y3. So the fermions are a tensor product of Pauli z's with either an x or y at the end. And from this perspective, we can see how big of a dimension of Hilbert space we'll need to realize these matrices. So if we want to construct n of these Majorana fermions, then well, if n was 2, we could get away with just 1 qubit. If n is 4, we need 2 qubits. And in general, we need n over 2 qubits. So these things can be realized in a Hilbert space of n over 2 qubits, n over 2 spin 1/2. So the dimension of the Hilbert space, which sometimes we'll refer to as capital L, is 2 to the power n over 2. So this is the place that we're going to be working in this Hilbert space. And for now, these Majorana fermions are just some collection of matrices. And their products form a basis for all of the operators acting on this Hilbert space. So, okay, so now we come to the SYK model. So far we've just described what Majorana fermions are in quantum mechanics. It's just this collection of n matrices. In the SYK model, we write a formula for a Hamiltonian where we use these matrices as building blocks for building up the Hamiltonian. So it's written as a sum of products of 4 of these fermions. And we sum over all possible terms involving 4 of the fermions, and we add them to the Hamiltonian with a coupling constant J I J K L. And the SYK model is defined by saying that this thing should be some set of random numbers. So more precisely, this is not a particular Hamiltonian. The SYK model is an ensemble of Hamiltonians. It's a type of ensemble of random matrices. It's a special ensemble which is constructed in this way. So what do we mean when we say that these are random numbers? So the simplest theory, and actually we'll use this a little bit in what I say today, is to define these to be drawn from a Gaussian ensemble with 0 mean and with a variance. So I'll use these angle brackets. Sometimes I'll write a subscript j, but I might sometimes forget. These angle brackets mean the expectation value in the ensemble of these random couplings. So that ensemble is defined for now as a Gaussian ensemble with 0 mean for these couplings and with a variance and with this variance. So the important thing here is this factor of j squared. So capital J with no indices associated to it is a parameter with dimensions of energy, and it just sets the overall scale of the Hamiltonian. This numerical factor is, just for convenience, the factor of 1 over n cubed here is important. What it means is that in the large n limit, in this model, things happen on timescales that are like of order 1. They don't take timescales that are of order n, and they don't happen on timescales that are of order 1 over n. That's accomplished if you put a factor of n here. Okay, so this model that I've written here is sometimes referred to as the Q equals 4 SYK model. That's a little q. So far we've discussed Q equals 4, and what that means is that we have 4 fermions participating in the interaction. But you can consider this for arbitrary even integer q. And the model behaves pretty similarly for various values of q. The exception is q equals 2. And that one is obviously sort of trivial because in the case q equals 2, we just have a quadratic term here. And this is a theory of n free fermions. We can make an ON transformation of our fermion psi to put the coupling matrix into a form that's like 0, some eigenvalue, minus eigenvalue, 0. In this block form. And then the fermions just become pairs of massive fermions that are not interacting with each other. So that model is a trivial limit, q equals 2. But for q equals 4, 6, 8, and so on, most of the properties of the model are quite similar. Okay. So from what I've said, you already know enough to explore this model numerically. And one of the kind of nice things about the SYK model, and I'm going to emphasize this perspective a little bit in the lectures, is that you can study it on a computer. And there are different types of things that you can do. And for now, one thing that you can do is just represent these matrices in the computer using tensor products of Pauli matrices. And then you can just sum up the Hamiltonian with the products of these terms. And to do large values of n, it's hard, and I don't know, you have to be a little bit clever to get into n into the mid-30s, but for like n equals 20 or something, you can just do this in any stupid way and it will work fine. And then you can start to calculate some things. So for example, the partition function at finite temperature, trace e to the minus beta h. You can compute this thing. Another thing that we'll discuss is the thermal 2-point function. So let's say psi 1 of tau. Now, these angle brackets with a beta here mean the thermal expectation value, not the J ensemble average. What this thing means is it's 1 over z of beta trace e to the minus Okay, so these are all completely explicit. You would sample from this distribution of J's to form the Hamiltonian, and then compute these quantities. And actually, I encourage you to try to do this. It's not hard, and for some purposes, it's useful. Actually, if you do want to do it, then one thing that will make it faster is to, in the matrix exponentiation, to diagonalize the Hamiltonian once and for all at the beginning, and then just do the matrix exponentiation using the diagonalized Hamiltonian. That's the, even if you don't do that, for a small enough n, you can do this anyhow. So there are a couple of things that, okay, I will now imagine that you have done that and explored this a little bit. And you could find two sort of interesting things. One is that this theory is what's called self-averaging at large n. And you can already see this in the numerics when n isn't even that large. What that means is that different realizations of the couplings here produce very similar results, both for the partition function and for these correlation functions. There are quantities that are not self-averaging, and actually we'll discuss an example of that in lecture 3, starting in lecture 3. But for most simple quantities, like these things, the variation from sample to sample is small at large n. It's suppressed by powers of 1 over n to the q.
So it is independent of this j?
Sorry?
It is independent of this j? Yeah?
Of which?
The j squared.
No, so this thing is a dimensional parameter that sets the scale of the Hamiltonian. If you like, you can set it equal to 1, and then you're measuring all of your times in units of 1 over j.
Is there some restriction on what j can be for these self-averaging? Like you put all entries 0 except for 1 on that.
Oh, yeah, sorry. I meant for the case which was defined here, where you take the couplings to be drawn from a Gaussian distribution with 0 mean and with this variance. And then the statement is that for almost all choices, for likely choices of couplings drawn from that distribution, the properties of the model will be very similar. You could get very unlucky and draw from the computer some crazy set of couplings, and then it won't be true, but that's very unlikely. Okay, so this is one property that you would discover by doing this numerical experiment. Another thing that you might discover is that the theory is sort of more interesting for large values of beta times j. So if you plot this 2-point function as a function of tau, so tau runs from 0 to beta. So this is the 2-point function in Euclidean time, and the Euclidean time is living on a circle of length beta. That's what it means that we're studying this theory at temperature 1 over beta. So the 2-point function is living on this circle. And here's the value 1/2. So if beta times j is small, then in this interval, the value of the correlator doesn't change very much. It stays very close to 1/2. But if the beta times j is large, then we get some curve that looks like that. So the time dependence of this correlator is more interesting when beta times j is large. And that's the regime where we'll be studying the model, is when beta times j is large. Compared to 1. So, so j is a parameter with dimensions of energy, and beta, the inverse temperature, has dimensions of length, so their product is dimensionless. And we can compare it to 1. So the interesting limit, most of the interesting physics in SYK is when beta j is much bigger than 1. And the theory is sort of easily solvable in the case where this is also much less than n, although the second restriction is not necessary. The theory can also be solved when beta j is much bigger than 1 and n is much bigger than 1 without any particular relation between beta j and n. For example, beta j could be bigger than n. The theory remains solvable. We'll discuss that a little bit later. Okay, so now we're going to start analyzing the theory in a more systematic way. So we'll start to do this by using the path integral. So forget about the representation of these fermion operators in terms of qubits. We'll think about this as an ordinary problem defined by a Feynman path integral. So if we want to study the thermal partition function, we define boundary conditions on the fermions such that they're antiperiodic. But otherwise, they're living on a circle of circumference beta. And this is the action. So this term here is just the free propagator for the fermions. And here's our interaction term, which is the Hamiltonian. And I'm assuming a sum over increasing indices I, j, k, and l. So we can analyze this theory by Feynman diagrams. So for example, the two-point function, the bare propagator for the two-point function is just, in principle, we could have different indices on the two ends, two fermions, I and I prime, but it's proportional to Kronecker delta, delta I prime, times sine of the difference of times over 2. So this is the term that we get by just taking the free propagator. So this one is the operator d tau inverse. But for the two-point function and the interacting theory, we should add further diagrams. And the diagrams that we have to study would include this one. We'll discuss that in a second. And then many other diagrams, including things that look sort of complicated, but I'll discuss the structure of them. And they're not so complicated. Things like this. Igor probably described these in his talk, I'm not sure, but these are called melonic diagrams. They're supposed to look, or iterated watermelon diagrams, or something similar to that. So let's first look at the first diagram I drew there and convince ourselves that this diagram survives in the large n limit. The point of these melonic diagrams is that these diagrams are the ones that survive in the large n limit. So they describe this model when n is large. An example of a diagram that doesn't survive would be one where we added some extra interaction like this here. That would be subleading in the large n limit, and we don't have to analyze it. But let me now just reassure you that this diagram survives in the large n limit. So we have an I here, and the fermions that propagate in this self-energy diagram can be of types j, k, and l. Then we'll have an interaction vertex at this point. So that will be j, I, j, k, l. We'll have an interaction vertex at this point, and the thing that survives the disorder average is when they have the same indices as I drew. And we're going to sum this over j, k, and l. So this term in the ensemble of j's that we've defined is proportional to j squared over n cubed. That was setting the variance of the distribution for the j's. And we're summing over 3 indices, j, k, and l, which will give us a factor of n cubed that, that cancels the 1 over n cubed there. So this diagram will be of order 1. And these diagrams are obtained just by sticking this same type of insertion anywhere on the internal propagators. So they will also be of order 1 in powers of n. So we have to sum this entire set of diagrams. Now, there's a Feynman diagram technique for doing this. And if you haven't seen it before, it might not look very simple. I'm not going to explain it too much because we're going to get the equations another way. But one way of doing it is the following. You write a symbol for the exact propagator that sums up all these diagrams. We write it as a propagator with a small dot in the middle of it. And then we write an equation that this thing is equal to the bare propagator plus a sum of self-energy diagrams involving big dots. Where this self-energy is equal to product of these renormalized propagators. So that's supposed to look, well, it's supposed to look somewhat intuitive in the following sense. The exact propagator will be a sum of diagrams with as many insertions as you like of this type of melon, where this melon itself on all propagators has as many insertions as you like of melons and so on. So in other words, the melons that you insert, the self-energy diagrams that you insert, will be built out of the renormalized propagators. The renormalized propagator itself will be a sum of self-energy diagrams involving those guys. So, well, if this is your first time seeing this type of Feynman diagram trick, it may not be very intuitive, but the equation, I'll get the equations that we get from this another way, so don't worry if it doesn't make too much sense. The equations that we get, let's write them over here. Are the following equations. So we define g of tau. Well, let me write it as g of tau, tau prime, to be the renormalized 2-point function. So the 2-point function of these fermions at temperature beta, including these interactions, summing all these diagrams. This thing is equal to the inverse of d tau minus sigma of tau, tau prime. So that one expresses this equation. That's a geometric series of self-energy diagrams where sigma is that big shaded dot. And that's j squared times g tau, tau prime to the third power. These equations are a little bit funny because one of them is a matrix equation, and the other one is like a pointwise multiplication equation. So we can think about this propagator with 2 time arguments as a matrix. And the first equation should be understood in the sense of a matrix. So this matrix is equal to the inverse of that matrix. But the second equation is like element-wise multiplication. Actually, in an unrelated context, last week, Nima Arkani Hamed referred to this multiplication as freshman's dream multiplication of matrices, where you don't have to worry about like whatever mnemonic you learn to multiply matrices together. You just multiply the components. Anyhow, that's why these equations are sort of funny, is that one of them is like a matrix and the other one is freshman's dream multiplication. Okay, so what we're going to do now is I hope simpler. So these Feynman diagrams are nice, but there's a way of thinking about the SYK model that makes the large N limit more manifestly simple. And that's what we're going to discuss next. And I apologize in advance because it's going to be a little bit unpleasant. The equations are simple equations, but they involve a lot of writing, and I've written them out in advance. But I think it's important to see the derivation of this next step. But just bear with me.
Did you use the randomness here?
Sorry?
Did you use the randomness here in deriving this?
Oh, what we used was we used the 2-point function of these j's. So, and that's where we used it. That's the only place we used that ensemble. So actually, as far as the 2-point function is concerned, it's not important that these j's be drawn from a Gaussian distribution. They could be drawn from any old distribution, as long as the mean is 0 and the variance is given by this, then we'll get the same answer. The fourth moment doesn't appear at leading order in large N.
So the suppression of the non-Mellon diagram relies on this average?
It relies on, that's right.
And are the equations that you wrote from Feynman diagrams, are those exact or are those just squiggles?
Which equations?
The ones
You're talking about these equations? Yeah, these equations are exact at large N. Yeah, sorry, I should have made this point more clear. So these equations exactly sum this set of diagrams, these iterated watermelon diagrams. And the justification for restricting yourself to these diagrams is large N. So at, right. So I'm not going to give too many references during this talk, but this discussion of the 2-point functions has been known in SYK and the SY model for a long time, since papers by Subir and Georges and Parcolet. Okay, so here's the derivation of the collective field description of SYK, which is the simple description at large N. And I want to actually explain it, so please do bear with me. So the idea here is that we're going to study the disorder average of the partition function, so the average over couplings J of the partition function. Now, we're not going to do replicas in today's lecture. We will discuss replicas later, but we're going to rely for now on the fact that was in this numerical observation that you guys did, which is that the theory is self-averaging at large N. So we'll just study the average of the partition function. We won't worry about replicas. So the average over J of the partition function can be written using our formula for the partition function itself by just doing the Gaussian integral over J. Now, how did the coupling J appear in that formula? It multiplied a 4 fermion interaction term. And when you do a Gaussian integral of like e to the j times something, then the Gaussian integral over J gives you e to the square of that thing. So that's what I've written here. So the term that J multiplied was a 4 fermion term, psi I, psi j, psi k, psi l, and it was integrated over time. And when we do the Gaussian integral over J, we get an expression where that thing is squared. And then the coefficient in front depends on the variance of J. So the variance of J was proportional to J squared over n cubed. We had this 3 factorial, and that explains this part of the expression. Okay, so now we do the first thing. We rewrite this term. So notice that the squaring is happening after doing the integral. That means that if we expand out the square, we'll have an integral d tau of 4 fermions and an integral d tau prime of 4 fermions. So it's a bilocal action. It depends on the fermions at 2 different times. And we can simplify that action a little bit as follows. We can write it as a term involving psi I, all to the 4th power. That's because in the second term, we have psi I, psi j, psi k, psi l, and we can just anti-commute the psi I term so that it's psi I of tau prime, so it's next to psi I of tau, psi j of tau prime, so it's next to psi j of tau, and then we'll get an expression like this. The numerical factor has changed from 3 factorial to 1 over 4 because this sum, we were restricting the indices to be in ascending order, and if we expand out this sum, the indices will be in any order. There's a difference of 4 factorial between those two those two types of sum. Okay. So far we didn't really do anything very interesting, but the first interesting step comes now. We introduce our first collective field, capital G. This is a bilocal field. It depends on two times, tau and tau prime, but it doesn't have any fermion indices associated to it. So it doesn't have any of the little I, J, K, L type indices. And the purpose in life of G is just to be equal to the average bilinear. I can remove this n here and put it there. The average bilinear of these fermion variables. Now this step looks funny because we're setting a G is an ordinary bosonic integration parameter, and we're setting it equal to like a bilinear of Grassmann variables. And that sounds like a funny thing to do, but it works. And it works if we interpret the delta function in the sense that we will in a second. Anyhow, if we have a delta function here that says G is equal to this bilinear of the fermions, then anywhere that expression appears, we can replace it with G. So let's look at the rest of this line. We have the free kinetic term. That just propagated through unchanged. And now our complicated bilocal term involving this funny configuration of fermions just becomes G to the fourth power. It's a bilocal variable, and it's integrated over both of its arguments, tau and tau prime. Okay, so now in the second to last step, what we do is we represent this delta function using an integral representation. So we represent the delta function as an integral over another bilocal field, sigma, which acts as a Lagrange multiplier that enforces this constraint. So in order to do that, we have exponential of sigma times the thing that we want to be 0. Okay, and actually in the integral representation of a delta function, you have to do the integral. Normally you would put an I here. We won't put an I here, and we'll just remember that the integration contour for sigma should be parallel to the imaginary axis. That's a perfectly fine thing to do. And then the integral over sigma of this first term in the exponential just gives us back this delta function. Okay, and then we just have these terms from before that carried over from the previous line. Now at this point, it looks like we've made a huge mistake. We started with some fermions. Now we have the fermions. We have these bilocal fields. The action doesn't seem to have got much better. But it got better in the following sense. The fermions now only appear quadratically. So we can do the integral over the fermions. Do the Gaussian integral over the fermions. And after doing the Gaussian integral of the fermions, we get something which is just a path integral over our new collective fields G and sigma. And I've written the action here. So this log determinant term is what you get by doing the integral over the fermions. Integral over Majorana fermions gives you a Pfaffian of the matrix of the quadratic form for the fermion action. And the Pfaffian is 1/2 the log, is the square root of the determinant. So we have half the log of the determinant. And this term here is just a slightly more compact way of writing the other terms. This one and this one. Okay. Now, I can put a closed parenthesis on my apology now for explaining this complicated story. But are there steps in the calculation that anybody would like to ask a question about? Yeah.
When you remove the n and divide it by it, do you just need to write that in the first place, or should there be some factor in n?
Oh, I haven't told you the normalization of these measures, so that will just affect that. Yeah. I'm sorry, I'm having trouble hearing you. Could you say the last few words again? Yes. Oh, yes, that's right, that's right. But we haven't got to that point yet. So, but that is the reason for the name, yes. Yeah, the question was why did we call them G and sigma? That's because as we'll see in a second, the saddle point equations for this action are just those equations we had for G and sigma earlier. Okay, so this is a weird and unfamiliar looking action. This part is bilocal and this part is non-local in terms of sigma. But for our purposes, there are two things that are good about it that are going to be important. The first one is that it doesn't involve any of the ON index I. So that's what it means that it's a collective field description. We started out by having n fermions, and now we have just these two fields, G and sigma. They're sort of unpleasant bilocal fields, but if n is very large, then that's an improvement. Having bilocal fields is an improvement over having n fields if n is very large. In particular,
one of them is n fields independent tau, and the other is two fields independent 2 others.
the reason why it's an improvement has to do with the second good feature of this action. Well, the counting we can argue about, actually.
There's no n from loops, right? That's what's good. Just the n is the n, that's it.
Let me not try to justify the counting argument, because I'm afraid we'll get into something unproductive. But there's a better reason why the collective field description is useful, which is that if n is very large, notice that the parameter n multiplies the entire action. So if n is very large, then this integral is a semi-classical integral. And we can analyze the integral by looking at the saddle point and looking at small fluctuations around the saddle point. And that makes the large N analysis very simple. We don't have to look at Feynman diagrams and like worry that there's some Feynman diagram we left out or something like that. We just study the saddle point of this theory and we study small fluctuations about the saddle point. Okay. So as an example of the saddle point discussion, let's imagine that we were trying to calculate the two-point function. In this theory, that's an integral 1 over z of beta times path integral over g over sigma. And so the disorder average, this will be the same thing. It won't depend on the index that we put here, psi 1. So we could put the index psi I and then divide by n, so we're averaging over the different flavors of fermions that we're correlating. And now the purpose in life of sigma, of G, is to be equal to this fermion bilinear. So this two-point function of the fermions just becomes equal to the expectation value in this theory of G itself. And at large n, this is approximately equal to the saddle point value, where G star is the saddle point of this action I. So let's now write down the equations for the saddle point of this action. By the way, regarding this counting, let's say we were trying to calculate the path integral, get some good approximation of the path integral at very large n, then one way we could do it is by discretizing time. And if we discretize time, we'll have something like, with time parameter epsilon, we'll have 1 over epsilon squared integration variables here. That's better if n is very large than n over epsilon, which is what we have in the description in terms of fermions. That's the sense in which it's a reduction in the number of degrees of freedom at very large n. Okay, so let's look at the saddle point equations we get. So if we vary sigma, then we'll get an expression from the log determinant, which is like 1 over d tau minus sigma. And if we vary sigma here, we'll just get g. So we get the equation g star is equal to d tau minus sigma star inverse. And the second one is even easier. If we vary g, we'll get a sigma from this term, and we'll get a g cubed from this term. And the equation is sigma star is equal to j squared g star cubed.
When you vary sigma, do you keep track of the fact that it's parallel to the imaginary axis?
You don't need to say anything about the contour in order to describe the saddle point. Okay.
Does the saddle point also have to be imaginary?
Sorry?
Does the saddle point have to be imaginary?
No. The saddle point can be anywhere. The contour is something that you choose. The saddle point is something that's determined just by the action. So these are the saddle point equations for this action. We didn't have to say anything about the contour. And again, I emphasize that this equation is interpreted as a matrix, and this one is interpreted as element-wise multiplication. So these are the same equations that we got by looking at the Feynman diagrams, but this approach is maybe a little bit easier. So still, they're not very nice equations. However, they are amenable very easily to numerical solution. And at the beginning of the talk, I described that you can study SYK model numerically by doing what's called exact diagonalization. You represent the actual Hamiltonian, and then you diagonalize it, compute the correlation functions, and so on. You can do that for like reasonably small values of n. But there's another way that you can study the model numerically, which is that you can study the G and sigma theory numerically. So you can solve these saddle point equations numerically. And in order to do that, the simplest thing to do is to assume time translation invariance. So these are functions only of the difference of their time arguments. And then this equation here becomes a simple equation in Fourier space. So this is an equation that looks like g of omega is equal to minus I omega minus sigma of omega. And this is now just an ordinary 1 over number kind of inverse. So you have one equation that's simple in position space, in time space, one equation that's simple in frequency space. And computers are very good at going between time and frequency space. There's an algorithm called the fast Fourier transform, which is very efficient for doing this. So you can represent the circle in time by, if you like 1,000,000 points, and you can solve these equations very quickly by doing iteration, where the iterative procedure, you start with the free answer. G is just 1/2 times the sine of the difference of times. And then you iterate by saying g of k plus 1. I'll explain this factor in a second. So this is an iterative solution of the equations where k is the answer after k iterations. G with a superscript k is the answer after k iterations. And a is a parameter that gives us a weighted update. So the weighted update is take whatever the previous iteration was and then add a little bit of what you would have got if these equations were, assuming these equations were correct. And if you take a to be small enough, like a is 0.1 or something like that, then this iteration will converge. It converges quite quickly to a solution to these equations. So that's how you can solve these saddle point equations numerically. Now, what do the solutions look like? So I'll draw here g of tau comma 0, g star. And as before, this lives on the circle where time runs from 0 to beta. And so if beta j is smaller than 1, it looks something like that. And if beta j is much bigger than 1, it looks something like this. Sorry? Yeah, okay. So why does it equal a half at 0? This is for the following reason. In quantum mechanics, when two operators are very close to each other, then they're separated by, we have some factor, like psi, so we have some product, psi of tau times psi of 0. So this product becomes something like e to the tau h, psi e to the minus tau h, psi. And if the separation between the times is small, then because this Hamiltonian here is, actually in our case it's a bounded operator, as tau becomes small, this factor just becomes 1. So we can replace this factor for very small tau by just our operator, psi, let's say this was psi 1, psi 1 squared. And psi 1 squared was equal to a half because of the relation psi I, psi j equals delta ij. So this is why it's equal to a half. And in general, in quantum mechanics, when the operators are very close to each other in time, you just get the answer in the free theory. In the free theory, the correlator is constant. It's given by a half. Okay. Other questions about this? Yeah.
Which n do you need to take in order to, in the numerics, in order to see the large n SYK?
Well, this depends on like how closely you want to see it. But n equals 20 is, you already see. I mean, it also it depends on how closely you want to see it, and also how low of a temperature you want to be able to see it at. And the value of n you need in order to get the very low temperature region increases as you make the temperature smaller. But if you don't care about getting very low temperatures, then like n equals 20, you would get pretty good looking curves. Okay. Now it's actually easy to get the solution to these equations analytically in a particular region here. When beta j is much bigger than 1, if we look in a region where tau is much bigger than 1 over j, and tau is much smaller than beta, then it's easy to solve these equations. And I'll just sketch for you briefly how this works. What we do is we guess that, I suspect that Subir discussed this in his lecture. Did you discuss getting the power law solution? Okay, maybe I won't repeat that discussion. But in this region, there's a simple scaling analysis of these equations where you drop the d tau term in this equation. You can show that that's self-consistent in this region. And you get an expression where g of tau is like sine of tau over tau to the 2 delta, with delta equals 1/4. If we had studied this theory with arbitrary q, general q, then we would have found this expression with delta equals 1 over q. That comes from a simple scaling analysis of these equations. Now, we don't need to make this assumption. Actually, we can solve these equations analytically just assuming this. The integrals involved are a little bit more complicated. But it's possible to check the following solution. G of tau comma 0 is equal to some number over So we have this solution. You can check that if tau is much smaller than beta, we recover this expression. But this one is valid everywhere where tau is bigger than 1 over j. So on this plot here, it would be valid in some region like this.
Can you get that from the reparametrization symmetry also?
Yeah, you can get it. You can get it that way. We'll discuss that in a moment. But you can also just get it by checking those equations are satisfied. You have to, I don't know, look up an equation for the Fourier transform of 1 over cosh t to the 2 delta. Okay. But if we plot this equation, this exact equation, we get something that will sort of follow the numerical curve for a while, and then it will increase with this power law singularity at the two ends. The curves are a good approximation for tau bigger than 1 over j, or smaller than beta minus 1 over j. Sorry?
Your J looks like a tau, but it,
Well, no, they're different. Okay.
people think it does.
That's a j. That's a tau. So. Okay. I'll try to write more clearly. Okay, so that's the two-point function. And we can in principle compare it to numerics. But there's another thing that you can do with this solution. And this was also done in the early days of studying this model by Parker and George and Subir. What you can do is you can take the solution, this solution, or the solution that you construct numerically at finite beta j, and you can plug it back into the action. You plug it back into the action, and you get a saddle point approximation to the integral that we started with, which is just the partition function. So this solution gives you an approximation to the partition function, which is good at large n. And you can use that to compute the free energy at large n, and you can do thermodynamics to compute the entropy as a function of the temperature or as a function of the energy. And this has a pretty cool feature, which was noted in those early papers. The feature is as follows. So what I'm going to write here is the entropy of the model divided by n. So it's the entropy per fermion. And the x-axis will be the temperature. So at very high temperature, this model is living on a very small circle, very small thermal circle, and the interacting term in the Hamiltonian doesn't matter. So we might as well have free fermions. It's related to the comment that here we just got the product of the fermions, which was a half. So at very high temperature, we just get the free theory result. The free theory result would be just, for the entropy, would just be the log of the dimension of the Hilbert space. It's a theory where the Hamiltonian is 0. The entropy is just the log of the dimension of the Hilbert space. So the entropy per fermion is log of 2 divided by 2. That's because the Hilbert space had dimension 2 to the power n over 2. So if we take the logarithm of that and divide by n, we get log 2 over 2. And this is about it's something like 0.35. Okay, and now we plot the answer that we get for all temperatures. So this should be true for a very high temperature. And the curve looks something like this. At 0 temperature, we get a non-zero answer, which is something around 0.23, if I remember right. Now this is somewhat surprising, that the entropy in this theory is non-zero, and in fact large. It's a fraction of n. So there's an extensive entropy in the system, even at 0 temperature in the large n limit. This led to some confusion, at least for me, because this does not imply that the model has an extremely high degeneracy at 0 energy. So one way you could get a large entropy at 0 temperature would be if you had a whole bunch of ground states. And those ground states, the log of the dimension of the space of those ground states would be this number. That's not what happens in this model. What happens instead is that this statement is only true if you take large N before you take temperature to 0. And what it really means is that near the ground state, you still have a high density of states. There's not a whole bunch of degeneracy there, but you have a high density of states that extends all the way down to the ground state. If you had studied the model with q equals 2, which is a free fermion model instead, then, so this is q equals 4. In the case q equals 2, you would have got a curve like this that does go to 0 at 0 temperature. And by contrast, in the q equals 2 model, there's not a bunch of states close to the ground state. Near the ground state, there's a gap, which I think is of order 1 over n. So it's sort of a small gap, but it's not extremely small. It's not exponentially small in n. The density of states near the ground state is small. In the q equals 4 model, it's not true. The density of states remains large, even near the ground state. That's what this 0 temperature entropy reflects. And it means that there's a lot of interesting stuff happening, even at low energies in this model.
And this number is universal, or it depends on the regularization of all this becoming continuous density of state?
This number, I'm not sure I really understand what ambiguity you're worried about.
There must be some regularization involved. If you say there's a bunch of many, many states which accumulates at 0.
It's not, no, there's, so this, let me draw a cartoon of the spectrum at some value of n, and I'm going to draw the density of states. It looks something like, I don't know, it looks something like this. I ran out of space, but something like this. So this is for q equals 4. And let me draw a plot now for q equals 2, and you'll see the difference. For q equals 2, the ground state is here, and it's very small. We get something like that. So near the ground state, the density of states is very small. In the q equals 4 theory, near the ground state, there's a lot of states almost immediately. Actually, as we'll see later, the density of states, the statement I made isn't quite true because this vanishes like square root of energy near the edge. But apart from that factor, the exponential factor remains non-zero at low energies. So the density of states looks like square root of e times e to the n times 0.23. So it's a large density of states even near the ground state.
Question was, it's a 0.23 universal. Yeah, I think.
Well, the point universal in what sense? Universal up to what?
Did it depend on any regularization scheme or not?
No, it doesn't.
I think at infinite n, this function is well defined. It's not defined at finite n, but it's well defined at infinite n.
Well, also, if you had a different Hamiltonian with a q equals 4 and a q equals 6 and a q equals 8, you had all of those terms, and they will not change the number 0.23. It only depends on the q. That's it. In that sense, it's universal.
Well, but if we studied q equals 6 by itself, we get a different number.
Yes.
So q equals 6 curve looks like this. Q equals infinity looks like this. So the density of states at low energies depends on q, but it's well defined. I'm still not sure I've answered your question, but if you want to, okay, yeah.
What would the entropy look like for large with finite n?
Yeah, it would go to 0 at very low temperatures. But what happens here? So yeah, I was planning to discuss this later, but it's a reasonable time to discuss it. So let me write a more accurate formula for the entropy. So the entropy as a function of this temperature. So and we'll study this for small temperature. Then we have an expression which looks like n times 0.23. And then we have a term which is not proportional to n, but it's minus, it's plus log of temperature over J. And then there will be terms plus of order 1 over n and so on. So at large n, we drop all of these terms, and we just keep this term. Then we find this result. However, this term can compete with the first term and can become large for very low temperatures. This becomes large and negative, and it reduces the entropy. And actually, it's possible to study this more accurately, where you resum a class of all of these 1/n corrections, and you find this formula for, well, not exactly this formula, but a formula with properties similar to this at low energy. The square root of E vanishing. Okay, yes? Sorry?
When you say the result for inflated Q,
Yes?
also
Yeah. So that's n is big first, and then Q is big. Okay. So we've said almost, well, probably more than you wanted to hear about just the analysis of the saddle point of this theory. And the next thing we should try to understand is fluctuations about the saddle point. So we'd like to understand the more about this functional integral space, in particular about the region near the saddle point that we just identified. That will be important for studying either 1/n corrections to this analysis or correlation functions in a power series in 1/n. These will depend on fluctuations of g and sigma around the saddle point. So we have to understand that. So here's a cartoon for the functional integral space where we have g and sigma. Of course, this is an infinite dimensional space. We have g of tau and tau prime, sigma of tau and tau prime. But I'm going to draw a cartoon here on the blackboard with just 2 dimensions. And let's say that our saddle point is here. Now, when beta j is some order 1 number, there's actually not too much we can say about this. But when beta j is large, so that's the low temperature regime where we got this 1/sine of tau to a power correlation function. It's where we have this feature. Then something interesting happens in the functional integral space. The interesting thing that happens is that there's a type of valley that runs through here, runs through the saddle point, where the action is very small. So along this valley, the action I is of order 1/beta j. In the other directions, perpendicular to the valley, the action is of order 1. And remember that in the g and sigma theory, we're multiplying this action I by n. And we're integrating over that. So, but in this region, it's proportional to n, but it's suppressed by a factor of 1/beta j. So at low temperature, these are the most interesting directions that we need to understand how to integrate over. The fluctuations of g and sigma in this direction will be much larger than the fluctuations in the orthogonal directions.
So then you have to come back and be parallel to the imaginary axis again?
Yeah, that's right. We should, yes, but for example, the integral, again, we don't need to discuss the contour in talking, for example, about the Gaussian integral about the saddle point, because there's only one contour where that integral makes sense. And we would have to discuss the contour for other more subtle issues, but not issues that we'll address here. Okay, so we have to understand this shallow valley and how to integrate over it. So this point here is called G star, and well, in principle G star and sigma star, and the points along the valley we'll write as G phi, and also sigma phi, but I won't write sigma. So what are these configurations G phi? Identifying these configurations was one of the many contributions that Kitaev made to this model. They correspond to the following functions. So we take the standard saddle point that we discussed before. This was 1 over sine of the difference of times to a power. And we make a reparameterization of the times by this function phi of tau. We also include a factor which reflects the conformal weight delta of the fermion. So this would be an ordinary reparameterization of a conformal correlation function by a map phi that maps our time circle to itself. So phi, so far, is an element of diff S1. These maps from the circle to itself. So we should ask whether this is, first of all, whether this map from functions phi to correlation functions g is a good map. And one thing you would like, for example, is that different functions phi map to different configurations g. That would make our life simpler in integrating, in trying to do the integral over g by doing an integral over phi. So in other words, the question is phi a good coordinate on this space along this valley? And the answer is no. It's not a good coordinate, but there's a small modification that will make it a good coordinate. The subtlety has to do with the following. If I define f to be tangent of phi of tau over 2, then this correlation function here, you can check that that's equal to it's equal to the following expression. So, for example, if phi was just equal to tau, we had a trivial reparameterization. Then f is just tangent of pi tau over 2. I should have put beta and pi. Tangent of beta tau over pi. Okay. Tangent of pi tau over beta. Then we'll get the expression involving 1 over sine pi tau over beta to the 2 delta. And in general, this reparameterization is equal to this function here. And now, something that's easy to check, the exercise that you guys have probably done many times, is to show that if we take f to af plus b over cf plus d, then this g will be unchanged. So it's SL2R invariant. So
Need a factor of beta in front of tan for this to work correctly.
I don't need that because it's independent of the rescaling of f. We can rescale f and it drops out. That's a special case of this transformation. So what this means, we can take two different functions f, which are related in this way, and they give us exactly the same correlator. Or equivalently, if we solve this equation for phi, we can have two different functions phi that give us exactly the same correlator. So phi, or f, is not a good coordinate on this space. However, what we can do is we can study phi, think of it not as an element of diff S1. We can think about it as an element of a quotient of diff S1. So a good coordinate is phi in, I'm only going to write this weird quotient once. The reason for this weird notation is that it's a quotient by a left action of SL2R. So SL2R could act on functions f of tau in two different ways, from the left or from the right. A left action would be this one here. A right action would be if we took f of tau and we took tau to a tau plus b over c tau plus b. However, the quotient that we want to do is by this transformation in f. This one does not, in general, preserve the form of the correlation function, so we don't worry about this one. This is the redundancy in description by f of our correlator. It's a left action of diff S1, so to get a good coordinate, we should think of phi, or f, as living in the space diff S1 with a left quotient by SL2R. So that's a description of this valley. And if you study the SYK model in the limit of large beta j, so where you drop this d tau term that Subir discussed in his lecture, and you get this simple solution, 1 over sine pi tau over beta to the 2 delta, then these configurations all have the same action. So in the large beta j limit, these configurations all have the same action. That's to say that this valley here is actually flat. So the functional integral over phi in that limit is completely unconstrained, and it doesn't make sense. We get divergent results because we're integrating over a function phi with no action. Yeah.
For finite values of ABCD, how do you understand this symmetry action on phi? So F has this transformation, how do you understand?
Yeah, you can solve this equation for phi. So you can solve, if we have a transformation for f, f is trivially related to phi, well, somewhat trivially related to phi, and you can solve it that way. So what we have to do to understand this theory at large but finite beta j, is understand the action at a good enough precision that we can get the non-zero value for the action in this valley. So we have to understand a 1 over beta j correction to the action. Now this is sort of a complicated story, and I'm not going to describe it in detail. What I'm going to do is write the answer for the action, and then we'll discuss some consequences of it, and I'll explain a little bit where it comes from. So the leading action as a function of phi on the valley Okay, so this is the expression that one finds for the leading action for phi along the valley. It's written in terms of the Schwartzian derivative of the function f that was this tangent of phi with respect to tau. That Schwartzian derivative is just this combination of ratios of derivatives of f. If you use the expression for f in terms of tangent of phi, this action, after integrating by parts, becomes this action here. This is referred to as the Schwartzian action, because it's built out of the Schwartzian derivative. So let's discuss some properties of this thing. So first,
What happens to tan?
sorry?
What happens to tangent?
Well, tangent is there, but if you plug the tangent in here and evaluate the derivatives, you get this expression. So first question is, does this action make any sense? So there's a couple of things that seem potentially problematic about it. First, we should check that it's well defined on this quotient space, SL2R mod, diff S1 mod SL2R. So that, in order for that to be true, we need this action to be invariant if we make a left action of SL2R. And indeed, that's easiest to see in this formulation. The Schwartzian derivative is SL2R invariant for transformations of f. So this action is well defined on the quotient, which is the space that we want to integrate over. So it makes sense at that level. There are some other funny features, like, for example, we have this phi prime in the denominator here. And you might worry, like, how do we deal with that? And this makes sense, well, first, it makes sense, at least in perturbation theory, expanding about the trivial reparameterization, phi is equal to tau plus some small correction, epsilon of tau. Then phi prime is 1 plus epsilon prime of tau, and it makes sense to expand this thing in powers of epsilon. Actually, it's not necessary to study the theory in perturbation theory. The exact path integral of this theory can be done. Okay, so
This is also invariant on the right-hand diffeomorphism?
no, it's not.
No.
It's not. So
So what does it change by? Total derivative or what?
well, if we make, for example, if we scale tau,
Yeah.
then the action rescales. So, yeah, this is an important point. We could have two different SL2R transformations that we're thinking about. One set of SL2R transformations are these SL2R transformations actually on the left, which should be thought of as gauge transformations. The redundancy in our parameterization of this valley. The action is invariant under those guys. Another set would be SL2R transformations of our physical time variable tau. Those would be like examples of physical conformal transformations of time tau. And this action is not invariant under that. This action breaks the conformal symmetry, the approximate conformal symmetry of the SYK model. So if you think about this saddle point solution that we had, the 1 over sine pi tau over beta, that thing has an SL2R invariance, where the SL2R is acting on tau. This action breaks that. So the theory does not have the SL2R symmetry. It doesn't have the physical SL2R symmetry. It has an unphysical SL2R symmetry, which is just a redundancy in our description, and doesn't mean anything.
So there is some scale which you introduced, or how?
Yeah, that's J.
That's J. So that caused the breaking.
Yeah, yeah. So, okay. That's related to a second obvious question, which is this formula for the action correct? So how does one know that it's correct? So there's a long and a short way of saying this. The short way is based on thinking about it from an effective field theory perspective. In the SYK model at large beta j, these equations where we drop the time derivative are reparameterization invariant. So we had this saddle point, and we have all of these other saddle points at large beta j, which differ from it by reparameterizations. Now, we're interested in the leading effect that breaks the reparameterization symmetry. The thing that breaks the reparameterization symmetry goes back to this d tau term in the equation of motion, in the equation for g. Or maybe even better, it goes back to the fact that the correlator has a maximum value at a half. So this 1 over sine tau behavior can't be exact. It can be exact only for tau bigger than 1 over j. So for very small values of tau, that's like the uv in this theory, the reparameterization symmetry has to be broken. So that means that in looking for a description of the effect that breaks the reparameterization symmetry, we should look for a local action, because it's a UV effect that's breaking the reparameterizations. We should look for a local action, which is a function of phi, and which has the left SL2R invariance. And then we can just use standard effective field theory reasoning. We write down the term of lowest order in derivatives that has that SL2R invariance, and that's the Schwartzian derivative. This is the lowest order local term with that left SL2R invariance. That argument does not fix the coefficient alpha. That's some number which you would have to fix by doing some calculation that knows about the explicit breaking of the reparameterizations. Now, to check the effective field theory analysis is sort of involved, but roughly what it amounts to is looking at the action near the saddle point and doing first order perturbation theory in the correction to the correlator G that results from this UV effect. You do first order perturbation theory in that action, and in that action for G and sigma that we wrote earlier involving the log determinant and so on, and you get this expression.
So you get the expansion in terms of epsilon, and you get the whole thing?
Well, you get the quadratic expansion But any reparameterization is small locally. So that actually implies the nonlinear function.
In the literature, there are a lot of words like almost Goldstone bosons. Of
Yeah.
While here you just told us that the breaking is explicit. Of the
Yeah.
So why?
Yeah. Thanks for asking this question. Let me try to answer it. Let's think for a moment about the theory without including this 1 over beta j correction. And let's imagine that we have this saddle point and we're looking at the fluctuations about it. The theory in this approximation has the reparameterization symmetry. So it has this full conformal symmetry, arbitrary reparameterizations by phi. Now, the saddle point that we've picked, 1 over sine pi tau over beta, that thing in that language would be a spontaneous breaking of the reparameterization symmetry. So we have the reparameterization symmetry, but we have a solution to these equations which does not have the symmetry. It has an SL2R subgroup, but it doesn't have the full symmetry. So then we can think of the field phi as describing the Goldstone modes that are moving us in the space of spontaneously broken reparameterizations. However, that theory is the integral over the Goldstone modes with no action would not be well defined. And we have to understand the leading term that gives those modes an action. The leading term comes from the explicit breaking of the reparameterization symmetry, and that's this term. So you can think of this term as the leading explicit breaking of the reparameterization invariance, and it gives you the action that describes this value. Okay. So there's a lot of stuff that you can do with this Schwartzian action. It describes many interesting properties of the SYK model at low temperature. Tomorrow we'll see that it's connected. This action is connected to a theory of two-dimensional gravity. But today, let me make just 2 points about it. The first is that we can understand some of the thermodynamics of the SYK model using this action. So to see how that works, let's look for the saddle point of this Schwartzian action. The saddle point up to an SL2R transformation is one where this epsilon is just 0. So phi is equal to tau. Phi equals tau, we get a 1 here. This term is 0. And the action, this Schwartzian action on the saddle point becomes 2 pi squared alpha over beta j. And this gives us an approximation to the partition function. That's e to the n times this 0.23 parameter that we had from before at low temperatures, plus 2 pi squared alpha over beta j. And this gives us an entropy as a function of beta. That's this 0.23 plus a correction term. That's 2 times this expression. And as a function of temperature, so 1 over beta is temperature, that gives us the initial slope of this curve. So we get the 0 temperature entropy, this value, without using the Schwartzian action from this 1 over sine tau solution. And we get the first correction to it, this linear slope, from the on-shell value of this action. Another thing that you can do with it is study fluctuations. So that was studying the actual saddle point of this Schwartzian action. But you can study fluctuations. And they give the leading contribution to, for example, the 4-point function in the SYK model. So suppose we look at a 4-point function of this type, where let's sum over the indices I and j and divide by an n squared. So we're averaging over two choices of the fermions. We have 2 of type j and 2 of type I, and we have them at 4 general points on the thermal circle. The approximation of the leading approximation for this 4-point function is just the product of 2 saddle point solutions. So at large n, this correlator factorizes into a product of 2-point functions. But at order 1 over n, we have a non-trivial term, a non-trivial 4-point term. And the leading expression for this f divided by the product of the 2-point functions is just a correlation function in the Schwartzian theory. So we have a term, let me write it in the following way. We have a term beta j times a function that I'll write as f big Okay, sorry for writing this somewhat large expression, but let me explain the terms. At large beta j, this term is larger. This is the biggest term. It's proportional to beta j. We have a beta j in the numerator because the action for the Schwartzian field phi was proportional to 1 over beta j. So its fluctuations are large. The fluctuations are of order beta j. This term represents the fluctuations in this Schwartzian field. These other terms come from other parts of the 4-point function representing the integral in the other directions along the valley. They're order 1 because they don't have any beta j enhanced fluctuations associated to them. These ones are, well, these ones cannot be computed in the Schwartzian theory, but let me just write how you calculate this big term, f big. F big is just an integral in the Schwartzian theory of g phi tau 1, tau 2 times g phi tau 3, tau 4. Yeah, actually. This is actually the full 4-point function. Sorry. This is the disconnected answer. G star plus 1 over n f big is equal to this expression. So this is intuitive to understand. We take 2 copies of the 2-point function. We reparameterize them by this field phi, and then we integrate over those reparameterizations with this action. That gives a simple function here, f big. So let me stop here. Let me just summarize a little bit what we discussed. So, well, I guess the SYK model is sort of like the story of a quantum mechanics model that tried to be conformally invariant, and it failed in a sort of big way, but an interesting way. So it tried to be conformally invariant in the sense that at low temperatures, it had this almost conformal symmetry. Arbitrary reparameterizations were solutions to the saddle point equations. But the fluctuations associated to those reparameterizations are large. And in order to get a finite theory, one has to understand the leading correction to the action that gives an action to those modes. That's the Schwartzian derivative action, and it's not conformally invariant. So it doesn't have the conformal symmetry in the tau variable, the physical conformal symmetry. So the SYK model ends up having, in the 4-point function, it has a big piece, which comes from the integral over this Schwartzian field, which is not conformally invariant. And then it has order 1 pieces. This term here is actually SL2R invariant. It has a physical SL2R symmetry. So the directions orthogonal to this valley can be treated in the strict beta j goes to infinity low temperature limit, where the theory has this conformal symmetry. So these terms are conformally invariant. But the biggest term is not. And that's the sense in which it failed in a big way. The attempt by the model to have conformal symmetry resulted in these large fluctuations that were themselves described by a non-conformally invariant action. And it leads to a large non-conformally invariant contribution to the 4-point function. Okay, let me stop there. Thank you. Yeah.
Numerically, if you're trying to find these saddle points you start, is there any risk that you're going to get stuck in this sort of valley and you find some having trouble getting to the right point?
Yeah, what will happen there is that the iteration will be slow. So the solution won't change very much. So the convergence will slow down. And that's something that you can see numerically. As beta j becomes large, the convergence of the solution to the final converged solution becomes slower. And that's associated to it moving along this valley direction.
But along most of the valleys, g is a bilocal function, not a function of two times.
Yeah, yeah.
Time differences, so
That's right, that's right.
iteration is only the time difference.
Well, depends which iteration you're doing. But Subir is right that if you're studying this model as a function of only the difference of the times, then you don't have this valley. That picks out a particular point in the valley, and then it's not a problem in the numerics. But if you study the full equations, like the full matrix equations, then you get slow convergence.